what we were looking at on Friday was the area underneath the curve y equals x squared. And you can see here on the right-hand side, there's the curve y equals x squared, which is a red curve. And if you decide to use the value of the function at the right-hand side of the interval, for example, this is broken up into 10 intervals, which are 1 unit wide. So what we're doing here is we're going to say the height of the rectangle, first rectangle, is 0 because the value of the function, actually we're using the left-hand value of the function. So it's the function at 0, which is 0. Then you evaluate the function of x equals 1, which is 1, and you multiply it by the width, which is 1. So the area of this rectangle is 1. The value of the function here is x squared, which is 2 squared, which is 4. So you take the height 4 and times the width 1, you get 4. This area is 4. And then you take the value of the function here at x equals 3, which is 9. 3 squared is 9. You multiply 9 by 1. And so this will be 9, 16, 25, 36, 49, 64. What's the next one? 81. Okay. So you add all those areas up. 1 plus 4 plus 9 plus 16 plus 25, etc. And you get, there we go. You get an area of 285. Now, if you use the value of the function at the beginning of the interval, so at the end of the interval, so the height of this rectangle is now going to be 1. Here, this one was 1. Instead of the height of the rectangle for this interval being 1, it's now going to be 4. And so the height of these rectangles is 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. And if you all add up all those rectangles, you get 385. So the answer is going to be somewhere between 285 because this underpredicts it because you've got these little empty spots that we're not counting, and you've got this overpredicts it. And if you average those two numbers together, so let's just take an average of the two areas, you would you get 285 plus 385 divided by 2, and I forgot to divide by 2. Divide by 2, and you get, whoops, still got it wrong. Okay, 285 plus 385. It's Monday. It's Tuesday. It's my Monday. Divide by 2. Okay, you get 335. So the average, probably the answer is close to 335 for the exact area underneath the curve. And if we increase the number of rectangles, if we double the number of rectangles, these areas would get smaller and these areas would get smaller, and these two answers would get closer to the exact answer. So what we're doing in our, what we did on Friday was we kind of set up the problem, and we said that what we're going to do is we're going to take the height of the rectangle, which is what we're just doing, multiply by the width of the rectangle, which we did, which is 1 in our case, and you add all those up, which I did, 1 plus 4 plus 9 plus 25 plus 36, etc., and for n equals 10. So the delta x for my example was we took the end of the interval, which was x equals 10, and the beginning of the interval, which was x equals 0, and you get a difference of 10, you break it up into n parts. So if n is 10, delta x is 1. Okay. Now, the value of x we use can either be, depending upon which one of those scenarios we use, this one says that at I equals, we're going to sum from I equals 1, it's going to be 0 plus 1 times delta x. So we're evaluating the function at x equals 1, which method is that? That's the second method. So if we go here, this one is evaluating the function at the end of the interval. That's what, if you use that particular counter equation. If you wanted to do, so this is at the end of the interval, end of interval. If you want to do it at the beginning, that would be the first example I gave. You would do x sub I is equal to 0 plus I minus 1 times delta x. So when I equals 1, you get 1 minus 1, which is 0, and you start at x equals 0. Whereas if you start at I equals 1 here, you get 0 plus 1 times delta x, which is going to be 1. So that's, and it doesn't matter which way you do it. We could go through this whole derivation using this way or that way, but when you take the limit as n goes to infinity, it doesn't matter whether you evaluate at the beginning of the interval or at the end of the interval, you get the same exact answer. So that's what I was demonstrating here. So you have to come up with some kind of counter, and it's just easier to use this one because it doesn't have I minus 1, it just has I. So that's the one that we're going to use to increment the value of x, just like I did conceptually earlier. Then you evaluate the function at the given value of x. So you take your function you're trying to find the area under, and you put in x sub I. So for x, I put in x sub I. But x, I use this equation. So for x, I put in 0 plus I delta x squared. So these are the height of the rectangles as I increment through the different intervals. And if I multiply this out, of course, I can just drop the 0. I don't have to use FOIL, just drop the 0. And you get I, which is a counter, not imaginary number. You get I squared and delta x squared. So that's the value of the function. That's the height of the rectangle. Delta x is, well, for delta x here, I can put in 10 over n. And also delta x here, I can put in 10 over n. So I do that twice because I've got to, for the value of the function, I've got I squared delta x squared, so that's f of x sub I, and this is delta x. That's the width of the rectangle. So for both of those, both for delta x here and delta x there, I put 10 over n. For my case, delta x was 1 that I showed you graphically. So for delta x, I put in 10 over n. I square it, I don't square it, and I have I squared. So once I multiply everything out, I get I squared, 10 squared, which is 100, times 100, which is 1,000. I divide by n squared times n, which is n cubed. So that's just simplifying this part in terms of I, which varies from 1 to n, and n, which is fixed. That's how many things I break it up into. Then what I can do is I can factor out the n and any constants outside of the summation, because this is for a given value of n, the given number of intervals, this thing stays constant. What changes as I increment through from I equals 1 to n is actually just I. So then what I did was I used one of the summation formulas. The summation from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. I think that's where we were. So now what we need to do is we just need to multiply this all out and simplify it, and then take the limit as n goes to infinity. I'm supposed to turn this thing off. Oh, that's the wrong thing. This thing. I think it tried. There we go. Okay. So let's multiply this thing out by itself so we don't have to. So we're going to evaluate this little numerator. So if we multiply n times n plus 1, we'll get n squared plus n. And then we multiply it by 2n plus 1. So I'm just multiplying the first thing out. And then we can use FOIL, and you get 2n cubed from this. Then you'll get FOIL is out, FOIL, so outer is n squared. Inner is 2n squared, and last is n. So if we combine like terms, we get 2n cubed plus 3n squared plus n. Okay, so now we can go ahead and put that into this equation. So we get 1,000 over n cubed times 2n cubed plus 3n squared plus n divided by 6. And we'll come over here and keep going. So now what we're going to do is we're going to take each one of these terms. So we're going to make up 3 separate terms. We're going to have the limit as n goes to infinity of 1,000 times 2n cubed over 6n cubed. So I'm taking this part and I'm grouping it with that part. And then I'm going to do the next one, which is the limit as n goes to infinity of 1,000 times 3n squared divided by 6n cubed plus the limit as n goes to infinity of 1,000 times n over 6n cubed. So we get three limits. And before we take the limit, we're just going to simplify these by canceling stuff out. So here I'll have 1,000 times 2 divided by 6. So that is 333.333. Okay, so this 2,000 divided by 6 is 333. And the n's cancel out. N cubes cancel out. So I don't have any, this first limit doesn't have n at all. The second limit, you take the limit as n goes to infinity of 3,000 divided by 6, which would be 500 times 1 over n. So you can see this n squared cancels out with n squared in there, so there's just n left. And then you have the final one, which is the limit as n goes to infinity of 1,000 divided by 6, which is going to be 166, times 1 over n squared. Now, once you take the limit as n goes to infinity of a constant, it's just equal to the constant. When you take the limit of 1 over n as n goes to infinity, you get 0, because you get 1 over infinity, which is 0. And when you take 1 over infinity squared, you get 0. So the answer is 333.33. That's the exact area underneath the red curve. And that compares with, when we had 10, what do we call, 10 intervals. We got area equals 285. We got area equals 385. This was when we used the rectangles below the curve. This is when we used the rectangles above the curve. If you average these together, you get an area of 335, which is pretty darn close to that number. So you can see that the number we came up with is reasonable based on what we've done already. So that's the basic concept here. So we're going to do another one, and then we'll probably only have time, we may not even have time to finish it, but then we'll let you work one in class on Thursday. Go get my, okay, so we already did that one. Let's try another example. Okay, so here's another one. So we're going to do the function y equals x cubed plus 1, which is sketched there, which it's a cubic, and it's just translated 1 unit vertically. We want to find the area underneath the curve between x equals 0 and x equals 3. So our limit definition for the area is the limit as n goes to infinity of n plus summation from n equals 1 to infinity of f of x sub I. Well, that's not to infinity, it's to n. So let's change that. And that should be I. I don't know why I did that. Made two mistakes there. Okay. It's summation from I equals 1 to n of f of x sub I. Okay. So we can well, the delta x part, we need delta x for two reasons. One is here, and also because when we evaluate that, we're going to have delta x involved. Delta x is equal to b minus a over n. In this new case, b is 3, a is 0, and n is just n. So you get, instead of 10 over n, you get 3 over n. So delta x is always just the interval divided by n. The width of the interval, I guess. Okay, then next thing you do is you do x sub I. That's going to be equal to a plus what is it? It's equal to, well, yeah, it's I times delta x. So it's I times delta x. So A is the beginning of the interval. So if we don't always have to start at 0. We're starting at 0 just because it makes life easier for this example, but we'll do some examples where A is not equal to 0. But for right now, while we're trying to understand the method. So since delta x is b minus a, when I equals n, you get to the end of the interval. So you integrate, not integrate, but you, I forget what the word is, increment. I can't get my shirt buttoned up here. So here's another funny thing that the girls did to trick us. So Sunday morning we get up and Judy goes upstairs to get dressed. And she's up there and she's up there. And so we go, what's going on? She's in trouble, doing something. You know, silence is trouble when it comes to that age. She's laying on the floor. I can't find my dress. What dress are you looking for? The long dress. She has this long dress they bought from Old Navy. It's got spaghetti straps. It's really not meant for the weather that we're having. But she loves that dress. She would wear that dress every day. So she has like her drawers, like she's picked through it. So I said, well, maybe it's in their dirty clothes. Let's go check it out. So we went to the dirty clothes. It was in the dirty clothes. And I said, well, we could wash it and that we could dry it and then you could wear it. Let me put it on just to fool Grandma. So, okay, we'll do that. Well, the fool was the granddad because she put the dress on and just left it on all day. It's like she wore her old dirty dress. Well, it wasn't that dirty, but it was, it needed to be washed. So she was tricky. We were like, yeah, okay, we're grandparents. We don't worry about things. If we were parents, we'd say, no, you have to take that off. We need to wash it before, blah, 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 blah. But, and then her mom washed it that night, and she wore it to school the next day with a sweatshirt underneath that wasn't appropriate. Okay. So anyway, this is, for our particular case, A is 0. So x sub I is just I times delta x. And then the value of the function, which in this case is going to be different, f of x sub I is going to be equal to, x sub I cubed plus 1. But x sub I is I times delta x. So we're going to, for x sub I, we're going to put in I times delta x cubed plus 1. And those are the three things we need because the area is equal to the limit as n goes to infinity of the summation from I equals 1 to n of the value of the function, which is going to be I times delta x cubed plus 1. So that's f of x sub I times delta x. And I'm just going to leave it at delta x right now. And then we'll go ahead. The next step is for delta x, we'll put in 3 over n. So you get the limit as n goes to infinity of the summation from I equals 1 to infinity to n of I times delta x. Delta x is 3 over n. We're going to cube that plus 1 times delta x, which is 3 over n. And then we multiply this out. So we're actually going to do that separately because it's a. So what we have is, well, no, we don't need to do that separately. We can. That's easy enough. This would be more difficult if a was not equal to 0 because then you have to do a third order. You'd have to do something cubed where you do have a first and last term, but in this case we only have one term. So if we multiply that out, we're going to get I cubed times 3 cubed, which is 27, divided by n cubed plus 1. The whole thing times 3 over n. And then we take the limit as n goes to infinity of the summation from n equals 1 to n equals I equals 1, sorry, I equals 1. I equals 1 to n, and if we multiply this times that, we'll get 27 times 3 is 81, so you get 81 I cubed divided by n to the fourth. So n cubed times n is n to the fourth. 27 times 3 is 81, I cubed. Then you get plus 1 times 3 over n, so we get 3 over n, like that. Now we have to go back and find the formula for the summation from I equals 1 to n of I cubed. So let's go back and find that. Oh, wrong way. Now if we had something to the fourth power, we'd have to have some formula for the fourth power thing, but we don't go that far. So but you would still follow the same procedure. Oh, that didn't work. Let's try it again. I don't know why sometimes it copies stuff and sometimes it doesn't. Edit, copy. There we go. You have to wait for that little thing to become highlighted. Okay. Okay. Paste. Okay. So there it is. It's equal to n squared times n plus 1 squared. So we put that in. So its limit is n goes to infinity of summation I equals 1 to n, and for I cubed we put in n squared times n plus 1 squared, all divided by 4. And then we have plus 3 over n. Okay, so let's multiply this thing. N squared times n plus 1 squared. That's going to be n squared. You multiply this out, you'll get n squared plus 2n plus 1. And then you multiply the n squared, you get n to the fourth plus 2n cubed plus n squared. So the area is equal to the limit as n goes to infinity of summation from I equals 1 to n of 81 over n to the fourth times n to the fourth plus 2n cubed plus n squared. And actually I did something, yeah, sorry, I messed up here. Not too bad. I got carried away here. Yeah, let's I can take the summation off of here. That's the thing. So when I replaced this, the summation part here, wherever it was, the summation of I cubed, I could replace it with that, so I had to get rid of the summation. And also, there's the other one we have to use here is, so let's put one space in here. The summation of C from I equals 1 to n is just C times n. So what this means is that at this point, this part becomes, instead of when I sum it, when I do the summation from I equals 1 to n of 3 over n, it's just 3 over n times n. So that's this summation here turns into that, the constant times n. That was the rule for the summation of C, which is just a constant. Okay, now we can go ahead and finish it. So we've got rid of the summation sign. So take the limit as n goes to infinity of 81 over n to the fourth times this thing, n to the fourth plus 2n cubed plus n squared. So that's that, this multiplied out. And then the last term is the n's cancel out, so you see that just is plus 3. And one last thing before we take the limit is we are going to divide everything by n. So we'll get 81 times n to the fourth divided by n to the fourth plus 2n cubed divided by n to the fourth plus n squared divided by n to the fourth plus 3. And actually I lied because I got one more simplification. So we get 81 and I forgot a 4 here, didn't I? Sorry. Yeah, 4. Put a 4 in there. So this 4 I forgot, so I put it back in now. So that's not too bad. Okay, so we got 81 over 4, and n to the fourth over n to the fourth is 1, plus 2 over n, plus 1 over n squared. So when you take the limit, these go to 0, and all you're left with is 81 over 4 plus 3, and 3 is 12 fourths. So you get 81 fourths plus 12 fourths, which is equal to 93 fourths. I think that's right. 93 fourths doesn't look right. So something's, but let me just. So let's go back and make sure. there's lots of rooms to make little mistakes. So we gotta make sure we do everything right. So you got to go back and check. Okay. So we got, this is the function. Put in x I delta x cubed. Okay, do that. That looks right. Put in 3 over n for delta x. Then 3 cubed is 27, I cubed, n cubed, plus 1 times 3 over n, okay. Then 3 times 27 is 81, I cubed over n to the fourth, plus 3 over n, that looks right. Then we take 3 times 27, get 81 over n to the fourth. Write out I cubed, summation of I cubed is n squared times n plus 1 squared over 4. 3 n. Okay, so this, the summation of this became that. The n's cancel out. I expand this thing out, plug that in. I didn't forget the 4. 3. Okay, I probably have worked out the problem. Let me see what I got. Well, actually I don't have it worked out. So I'm going to show you something just for your information. This is how I check to make sure I do my problems right when I make up a test, is I go online. And you can, there are actually things that do all this for you. Well, it doesn't do it this way, but it does it other ways, but it'll check my answer. So if you go to Google and you put in definite integral calculator, and that looks good. And you can put in your equation. So my equation is x cubed, and I integrate, actually it's x cubed plus 1, gotta go back here, plus 1, and I integrate, I didn't like that, let's try it, integral. Okay, I integrate from 0 to 3. There it is, x cubed plus 1, integral from 0 to 3. You'll see why this is true later. I'm just checking my answer, so if I made a mistake. 93 fourths. Hey! I got it right. Okay, so I did do it right. Obviously, what I just did there online is a lot easier than what we're doing here, but that's the whole purpose here. Is what we're gonna figure out is that there is a much easier way of doing this, but we have to suffer through the long way just to be able to show what to demonstrate that when you add all these rectangles up, and you take the limit as n goes to infinity, you don't get an infinite answer, you don't get a zero answer, because you might think, I've got infinite number of rectangles, therefore the answer must be infinite. But because the width gets smaller proportionally, it all comes out in the long run when you take the limit. Actually, this is from previous. That was from last year. Okay, this was to show you how the easy way of doing it. Okay. So here I'm going to demonstrate. Sorry about that. So anyway, we came up with the answer. Where did I do it? Where's my answer? I did that. Oh, there we go. There's the answer. Okay, this is my previous year's solution. Okay, so let me delete that. Delete page. Okay, what similarities did we see between the derivative and the area derivations? So we set up the problem using small finite values. In the calculation of the derivative, the small value was the difference in the y value and the difference in the x value. We took the limit as the width delta x got smaller for the derivative, and we took the limit as but for the integral, we took the limit as the number of rectangles went to infinity. So in one case, we let delta x go to 0. Here, we let n go to infinity, but we're still doing a limiting process. And another common thing is a lot of the terms dropped out because they ended up being 0 when you did the limiting process. Now, in the case of a derivative, if we started with a polynomial, we ended up with another polynomial. Also, for the that should really say derivative, not derivation. Derivative. For the derivative, what we ended up with was an indeterminate result. We had delta y went to 0 and delta x went to 0, but the indeterminate result actually went to some finite value. In the area case, we end up taking the width to we take the number of rectangles to infinity, but we take the width of the rectangles to 0, and so it's kind of 0 times infinity, which is another kind of indeterminate result. And we use the limiting process to get rid of the indeterminacy, just like we use the limiting process here to get rid of the indeterminacy. So you can see that, hopefully see the similarities between the two. Okay. Now, what I'm going to show here is if I were to, this is what is called taking a definite integral. So I'm going to take the function that I was trying to find the area under the curve for, and I'm going to take the antiderivative of this, which is easy. So to take the antiderivative of x cubed plus 1, you add 1 to the exponent, divide by the new exponent. Here we have x to the 0, so you add 1 to the exponent, divide by the new exponent. So if I take the antiderivative of x cubed, I get x to the 4th over 4 plus x. And if I evaluate the antiderivative at 3, I'll get 3 to the 4th plus 4 plus 3. 3 to the 4th is 81, so I get 81 over 4 plus 3. If I evaluate the antiderivative at 0, I'll get 0 to the 4th over 4 plus 0, and you get 0. And so the antiderivative at 3 is 93 over 4. And the antiderivative of 0 is 0. And you might say, wow, that's a coincidence. The area I got by using the limit process which was 93 over 4, is the same as the antiderivative evaluated at the upper limit, the left right-hand side that of the area, minus the antiderivative evaluated at the beginning of the interval. If I subtract those two, I get the area. And you're like, ooh, that's pretty cool. I wonder if that's just a coincidence or if there's something to that. It turns out that's what Newton figured out. And we'll talk about this in section 4. The fundamental theorem of calculus basically says instead of having to go through this long, complicated, easy to make mistakes procedure, if I actually take the antiderivative of the function that I'm trying to find the area underneath the curve, if I take the antiderivative and evaluate the antiderivative at the end of the interval and subtract the antiderivative evaluated at the beginning of the interval, I get the same number. So which is easier, right? Obviously, this is a lot easier, but we still have to prove that this is true, and I've proved it twice. Well, almost proved it twice. I proved it once because I actually did this, but we need to practice a few more times just to drill it into our skulls. So I'm going to go ahead and assign the homework. There's only 4 problems because it takes a long time. And that reminds